Okay, hello everybody. Did everybody submit their proposals? Do you guys all, have you turned those in? Yeah? Okay, so we are on our last lecture today on first order methods, so you can say goodbye to them pretty soon. Just to review quickly what we did last time. Let's see here. Last time we talked about this thing called generalized gradient descent, which was essentially doing gradient descent, but when we split up the objective function into two functions, g and h. So this was our setup here. We thought that f was equal to g of x plus h of x. G was a smooth function and h was non-smooth, but it was simple. And we used the same motivation that we had for gradient descent, where we used a quadratic approximation at each iterate of the algorithm, but in this case we actually only expanded g and not h. And that's how we basically derived this generalized gradient descent algorithm. Okay, so here was the very basic derivation. We replaced g by g hat, where that's the quadratic approximation to g, and then we choose the next step in our iterative process to minimize this. We didn't touch h, but we expanded g. And we defined something called the prox function at the top here, which has to do with the function h, but nothing to do with the function g. And it's the following minimization problem. You give it an x, and your job is to find, you're given an x, and your job is to find a z that minimizes this criterion. It's like just a very simple squared error to x plus h of z. And if you can do that, if you can evaluate the prox function, then you can do generalized gradient descent. Okay? So given this definition for the prox function, generalized gradient descent looks like this. We basically just iteratively repeat this, apply this prox function to our current point minus t times the gradient along g. And we had kind of a couple quick examples. If h was 0, then this prox function is just the identity map, right? You give it x, it gives you back c. So this generalized gradient update, this is exactly gradient descent. It's no different than gradient descent. And we also talked about what happens if we had the one norm for h, and we derived this algorithm called ISTA. So in this case, the prox function is just soft thresholding. Okay, and we have this algorithm that just repeatedly soft thresholded. Basically, when we had squared error loss for g, something like x plus the inner product of all of our predictors with the residual vector. Okay. Then we had this nice result that said that after k iterations of the algorithm, we get 1 over k convergence rate, just like gradient descent. And we actually proved this last time too. And in this case, it was important to remember here that these are iterations of the algorithm. These aren't like operation counts. And each iteration of the algorithm is an evaluation of that prox function. So if that prox function was complicated, then each iteration could be costly. So that's something to remember. The comparison to gradient descent, where an iteration is just compute the gradient and take an inner product, is not necessarily a fair comparison if the prox function is really complicated. And we had this example of matrix completion, which we're going to revisit today again, but I'll just kind of quickly go over what that was. In this example, we observed only some entries from a matrix. We only observed, say, the entries I, j that were in some observable set omega, and we wanted to estimate what the other entries would be. And some of the applications you might have in mind would be like the Netflix prize here. So we looked at this minimization problem here. It splits up into g plus h, right? G is the smooth part. We take the square differences between aij and xij. Xij is our variable over all ij that we observe. And we add something that's the nuclear norm of x times lambda. And this nuclear norm, it approximates the rank of x. Okay, so this is saying like I want to fit well to A, but I want to penalize how complex that matrix X is in terms of its rank. So this is kind of like the matrix version of the lasso. That's how we thought of it. And when we went through the steps and we derived the generalized gradient algorithm for this problem, we saw that we could actually take the step size equal to 1, because the Lipschitz constant here was 1. So our convergence analysis told us that we could take the step size equal to 1 over the Lipschitz constant, and that's 1. And the algorithm simplified into this very kind of this very natural update rule, which says that take the entries that we observed in A, add all the entries that we didn't observe, but only take the ones from our estimated vector x. So we form this matrix by putting those together. And then we do this rank reducing step here. This is a matrix soft thresholding. You can think about it like we're rank reducing. Okay, so we just repeat that over and over again, and it converges to the solution of that matrix completion problem that I wrote up. And I also said that this appeared in the literature as an original algorithm called the soft impute algorithm. And it's pretty scalable, and people are starting to use it for matrix completion. Okay, why don't we, do you want to collect the proposals? If people have proposals they haven't turned in, we're going to collect them now, so make sure you get those in. Okay, he can just drop it off then. Okay, so we're just going to finish up with a couple of lectures on generalized gradient descent, and then we're going to move today into acceleration. That's going to be the last topic that we cover among first-order methods. So why is it called generalized? Right, there's that term generalized gradient descent, and it's called a bunch of different things. You might find this in the literature as proximal gradient descent. Some people also call it composite gradient descent, but I like to call it generalized gradient descent. This is not my name. I like to go by this name, because it kind of indicates that several special cases of this algorithm give us a bunch of algorithms that we already study. Okay, so it's kind of like a general framework for all the descent methods. So we already said if h is 0, right, if I think of f as g plus h, where g is smooth and h is non-smooth, if h is 0, then we get gradient descent. And the prox function is just the identity map. So we get gradient descent. Okay, if h is the indicator vector of some set C, then we get projected gradient descent. Okay, so that's how we do gradient descent with a constraint set, as long as we can do the projection. And we're going to talk about that shortly. And if we take g equals 0, another special case, then we get something called the proximal minimization algorithm. Okay, so this is an alternative to, say, the subgradient method for minimizing non-smooth functions. Right? Because here, if g is 0, f is just h, and it's non-smooth. Okay, so these are three pretty well-studied algorithms, but we've actually proved that all of these algorithms have a 1 over k convergence rate, because we've proved it for generalized gradient descent. So now we can go ahead and use any of these, and we know how they converge. So that's a nice result of studying this general problem. So projected gradient descent, I'm thinking of I have a closed convex set C, and I want to solve the following problem. I want to minimize over all points x and C this smooth function g. Okay, and how do I write that? I can write that as minimize over all points x unconstrained, g of x plus the indicator function of x being in C. Right, and we define this to be 0 when x is in C, and it's infinite when x is not in C. So those two are definitely the same problems. So what's the prox function here? The prox function, you specify an x, and now you have to find a z, which minimizes this problem. It minimizes the distance to x plus the indicator function of being in C at the point C. Right, so what is that? That's just equal to the minimum over all points z in C of the distance to x. Right, because if z wasn't in C, this would be infinite, so we'd never achieve the minimum. Right, and what is this? This is exactly the projection of x onto C. I'm just finding the closest point in C to x. So the prox function is just the projection operator. So what happens when I repeat my gradient update steps? It usually looks like x plus is equal to the prox function of x minus t times the gradient, but here it's just the projection onto C. Right, so this is projected gradient descent. What do? We make an update not respecting the constraints. We just look at the gradient and we make the update as usual. And then we project back onto C so that our point x plus is feasible, that it's in C. And we repeat this over and over again. Okay, so here's a picture of what that might look like if, say, this red diamond is our constraint region. This is C. And these are the contours of our function g. Okay, and the minimum maybe is over here somewhere. So if we're at this point, we look in the direction of the negative gradient. We take a step there. But now we're not in C anymore, right? And we want to minimize the function g subject to being in C, so we just project back onto C. And that's what this does right here. Okay, and we'll repeat that over and over again. So we've actually proved that this method converges and has a convergence rate of 1 over k. Right? Provided we can do that projection, we can go ahead and now do gradient descent with constraints. Are there questions about that? So here's just a quick survey of some sets that are easy to project onto. So affine images are an example of sets that are easy to project onto. The solution set of linear systems, something like if I just say that I want x to be positive in every coordinate, right? What would the projection be for this one, for example? It would just be I take x, and if it's ever negative, I just move that component to 0. Otherwise, I leave that component untouched. That's the projection, right? These ones have to do with the inverse of A, basically, or the inverse of A transpose A, or AA transpose. I think if you thought about this, you could definitely write out the solutions to these ones on a piece of paper. Norm balls are not easy to project onto, but it's possible. Actually, the 2 norm is quite easy to project onto, right? We just take a vector, and then we just divide it by its norm. The 1 norm ball is not easy, but there are linear time algorithms to project onto. You could find that in the literature, and we can just go ahead and plug that in. And the infinity norm is also easy to project onto. And I'm just going to be very vague here. Some simple polyhedra and some simple cones are also easy to project onto. So I didn't want to spend a lot of time on this, but this just gives you a flavor of what you maybe can expect to be doable for projected gradient descent. But it's important to remember that it can be very easy to write down a simple set C for which the projection is very hard. So an example is if I just tell you, my microphone still on? Okay. If I just tell you that I have an arbitrary polyhedron C that's defined by some set of linear inequalities, it's a set of all x for which A times x is less than or equal to B in every coordinate, that's generally a very hard problem to solve in terms of the projection. That's almost no easier than the minimization problem in the first place for an arbitrary A. Okay, so you have to be careful about using projected gradient descent. You have to use it in a case where you know how to do the projection properly. So what's the other special case? The other special case is something called the proximal minimization algorithm. It's when g was 0 in that decomposition. So now we want to minimize for a convex function that's not necessarily differentiable, minimize h of x. Okay, so we had a method to do that. That was the subgradient method. Remember, we just did essentially the same thing as gradient descent, but we replaced a subgradient of h with the gradient and the usual gradient update. An alternative is just to try to repeatedly solve this. All right, let's just repeatedly use the prox update. It looks like this. This is called the proximal minimization algorithm. We've proved that if the prox can be evaluated, this converges at a rate that's an order of magnitude faster than subgradient descent. But we have to know that we can actually evaluate this prox. Okay, so it's faster than subgradient method, but it's not nearly as general. It's only implementable if we know how to evaluate the prox in closed form. Okay. So then you might think in general, not just for the proximal minimization algorithm, just in general, when we're doing generalized gradient descent, what happens if we can't evaluate the prox? Where can we actually use the algorithm? Where can we go from there? Everything we've done so far in terms of our convergence rate, it's assumed that we can evaluate the prox exactly. And generally speaking, if we don't know how to evaluate the prox function and we just treat this as another minimization problem, so we actually say, okay, let's use another one of the tools from this class to solve this problem, and we'll maybe get another approximate solution. We'll plug that in each step. If you do that, then generally speaking, all bets are off. Right? We don't have a very precise statement for saying how fast that converges, because we're assuming that actually there's no error in approximating the prox function, that we actually know it exactly. There are exceptions both in theory and practice to this. Sometimes you can get away with a noisy prox update, you might call it, a prox update that's not perfect. And I gave a nice example of a paper here that does something called partial proximal minimization by two kind of very famous authors in optimization. That's an exception to this. So it's something that doesn't actually evaluate the prox exactly, but both in practice and in theory, it works very well. Okay, but just in general, we can't treat this as another minimization problem unless we can say something very special about what we're doing here. Okay, so yeah, there's a question there.
Yeah, so for the projected gradient descent, does it solve the prox exactly the question? How does it work?
Yeah, so in the projected gradient descent, the prox function is the projection operator. So if we know how to project, then we're solving the problem exactly. By exactly, what I mean here is you can think of there's kind of two types of error. There's maybe something like numerical accuracy error that's due to a computer. So if I were to plug in one of these projection algorithms into a computer, it might give me kind of not the exact answer I'm looking for. That's not what I mean by approximate. What I mean by approximate is something iterative. Like suppose we were to actually attack this prox problem by another iterative algorithm that we learned later in class, or suppose we could take the dual of this after we learned duality, and then we've just used another first-order method to solve the dual of that. That's what I mean by an approximate method, something that actually, even if we had perfect computer precision, would still not give us a perfect answer. That's a good question, though. Okay, so we're almost at the cutting edge for algorithms within the class of first-order methods, but we're not quite there yet. And if you remember that at the very first lecture on first-order methods, we learned that there was a lower bound for the convergence rate of any first-order method over the problem class that we're interested in. And I claimed back then that we can achieve it, and we're going to see now how we achieve it with something called acceleration. So the idea behind acceleration is that at each update, suppose we want to compute xk, we're going to use more than just xk minus 1 to inform us of where to go. For example, we might use xk minus 2 as well. And this usage is sometimes called a momentum term or a memory term. You'll see those kind of used interchangeably. There are many different flavors of acceleration. So we're going to learn one. But there are at least three that I'm aware of, and there may be more. And they're mostly due to one person, Nesterov, who's the same person who provided us with those lower bounds. So this person has been somewhat dominant in the field of first-order methods for a little while. And we're going to see that actually we can use acceleration to accelerate the generalized gradient method, not just the gradient method, to the rate of 1 over k squared. So not only can we achieve a rate of 1 over k squared, we can actually do that for problems where the function decomposes as smooth plus non-smooth as well. Okay, and we're going to get to that today. Okay, so I basically said this. I'm not really going to go over this again. That's generalized gradient descent, and today we're going to improve its convergence rate by an order of magnitude using something called acceleration. So here's a little history of acceleration. It's a very modern topic. Like I said, I hinted at last time that the next two lectures were going to be kind of much more modern than the first two on first-order methods. So there's basically four ideas surrounding acceleration. And there's really three acceleration methods, and one of the ideas just uses smoothing in conjunction with acceleration. And they're all in this case attributed to Nesterov. And there's four papers that Nesterov's written, and I have all the references at the end in case you're interested in actually reading the original papers. Some of them I would say are not too bad to read. Others are quite hard to understand. So don't get discouraged if you try to look through these papers. They're not written in a way that's it's immediately transparent as to what's going on. That's partially why it took people so long to appreciate acceleration too. So 1983 was the original acceleration idea for smooth functions. Nesterov had this paper that said, if I just have a smooth function, I can actually achieve an order of magnitude faster than gradient descent in terms of my convergence rate by applying acceleration. In 1988, he has another acceleration idea. Those are actually two different ideas. In 2005, this paper is a smoothing technique that he proposes for non-smooth functions. So you smooth a non-smooth function, and then you apply my acceleration idea of 1983 to that newly smooth function. And in 2007, there's this acceleration idea for composite functions. So this is the most relevant one to us because it's kind of the most general. If we have f equals g plus h, this 2007 paper offers a prescription for how to accelerate generalized gradient descent in that framework. Then there are two other authors, Beck and Taboul. They extended the original acceleration idea of Nesterov in 1983 to composite functions. So it's in the same setting as this 2007 paper, but actually I think this one's a lot easier to understand if you read it. And they're different ideas. So there are different ways you might think that you could extend the smooth idea to composite functions. These two are not equivalent. So they're different ideas. They actually have the same convergence rate, but in terms of practical implementation, they're very different. And it's going to probably make more sense as we continue with the lecture, but I'll just say what the difference is now. The one we're going to learn today, it uses a one-step history. So it uses the iterate that we're at and the previous iterate, and then one step beyond that, which is xk minus 2. This idea of 2007, it uses what's called an infinite history. So it uses all of the iterates from x1 to the current point. So they have very different update rules in terms of what you're keeping track of and keeping around. And these authors, I think, are sometimes not credited with the idea of acceleration because they kind of extended Nesterov's original 1983 idea, but it's important to kind of give them credit because, like I said, this is truly different than Nesterov's proposal for composite functions. So this is the one we're going to learn today. There's a lot of literature on this, and it's somewhat scrambled, so I put as many of the references as I could at the end in order, and you can go through them if you're interested after the class at some point. Oh, and also, Paul Sang, he has an analysis of all of these acceleration methods in one paper. He tries to kind of unify them together into a single framework. So that might be helpful to look at. So here's what we're going to talk about today. We're going to talk about acceleration for composite functions because it's kind of one of the most general prescriptions for acceleration. We're going to learn this method of these two authors I mentioned. And I like the presentation that was given in some lecture notes by Lee Vandenberg, so we're going to follow that presentation as well. We're going to state its convergence rate. I'm not sure we're going to actually prove it today. I might survey the class to see how interested people are in seeing the proof. Then we're going to talk about something called FISTA, which is what happens when we take ISTA and we add an F. It stands for fast. So we're going to apply acceleration to ISTA. And then we're going to kind of talk about this important point here. Is acceleration always useful? So here's the basic idea. We're just going to go ahead and state it. We have this composite problem. G is smooth and H is non-smooth. They're both convex. And we're going to talk about the accelerated generalized gradient method. And it looks like gradient descent, but there's an important distinction in terms of which point we make the gradient update on. So now we're actually going to choose two initial points, x0 and x minus 1, and we typically just make them equal. And we're going to repeat the following steps. And the first step, we're going to define a new point y. And this is an auxiliary variable that only exists for this particular iteration. And it's equal to xk minus 1 plus a multiple of the difference between xk minus 1 and xk minus 2. Okay? So it's taking something about some information in terms of where we've been, plus the current point. And we have some cleverly chosen weights here that are actually pretty crucial in terms of the convergence analysis. If we had the wrong weights here, this wouldn't work. So this is part of the cleverness in the method, is also choosing these weights to work just right. So that's the point we consider y. Instead of xk minus 1, we're considering y. And then we go ahead and we actually just do the usual generalized gradient update, but on y, and not xk minus 1. Okay, so we take y, we subtract off a multiple of the negative gradient at y, or we add a multiple of the negative gradient at y, and then we take the prox function of that. So here's kind of just a little overview of what happens at k equals 1. Right, so if I'm at the first iteration, then I remember I've chosen xk minus x0 actually and x minus 1 to be equal. So y is just equal to x 0, right? Because I have x0 plus, in this case it would be 1 minus 2 over 1 plus 1 times x0 minus x minus 1. But those are the same. So I just do the usual generalized gradient update at the first step. Okay, after that I'm doing something a little different, and here's a little picture of maybe what's going on. So let's suppose I'm at xk minus 1, and this is where I was before, xk minus 2. In generalized gradient, we would actually take this point and we would move in the direction of the negative gradient of g here. And then we'd apply the prox function. In accelerated generalized gradient, we take this point and we look at the direction that we were going to get there, and we add a multiple of that to this point. Okay, and that multiple is always less than 1, so we're going to be adding something, we're going to arrive here. This is why some people call it momentum term, because it pushes us in the direction that we are going from the previous iteration. Okay, it encourages us to keep going in the direction that we just were heading, and then we make a gradient update here. So maybe that moves us in this direction, whereas the gradient here might have pointed us there. And the hope is that by using this momentum, that we're actually speeding up the algorithm. Okay, so that's a very kind of rough overview of the intuition behind acceleration. I think people admit that acceleration is not very transparent. Like this is kind of an explanation for what happens, but this is not bulletproof, right? You might think that, well, I might be going the wrong direction, so why is it helpful for me to accelerate in the wrong direction? So there is something missing, I'd say, in terms of the intuitive explanation for why acceleration works. And I don't think that there's a generally very good explanation for the intuition behind acceleration. The proof is, it works out basically, it works very carefully on these constants to show that we actually don't ever mess up, that we can achieve a 1 over k squared rate, and that this doesn't hurt us. I don't think the proof is terribly enlightening either, which is why we might skip it. But let's just go through with the gradient method from now on, and we'll see how things go. So here's what these weights look like. These weights, k minus 2 over k plus 1, is a function of k. You can see that the weights get closer and closer to 1 as k gets larger and larger. So what does that mean in terms of the amount of momentum we're applying to the algorithm? Are we accelerating more at the start or the end of the algorithm's run? The start? Well, let's look at what we're adding. Okay, we're starting with xk plus 1. We're adding some multiple k minus 2 over k plus 1 times the direction that we just traversed to get to this point. So if that constant is close to 1, are we kind of accelerating more or less? More, right? So these are chosen so that at the start, when we might not have a lot of information, we're not going to be kind of rushing off too quickly in the wrong direction. But hopefully as the algorithm progresses, when we're closer and closer to the minimum, we're going to be accelerating more and more. So here's an example of acceleration. I had to take this out at the last minute because I realized that you guys have a homework problem that'll be posed tonight on logistic regression, and I almost gave away the answers. I was very close to giving away the answers. So let's consider minimizing f of x equal to what you're going to derive for us on your homework, which is the logistic regression loss. And this is a smooth loss. We have no penalty here. It's just logistic regression. And its gradient is something. And you're going to also compute that for us on your homework. After you turn your homework, I'm going to update the slides so you can have a reference for this. But for now, it'll be censored. There's no non-smooth part here. Okay, so the prox function is just x. So I'm just doing accelerated gradient. There's nothing really generalized here. Okay, so this is just a simple example of acceleration. So here's an example where I had 30 observations and 10 variables. Yeah?
Wait, if the prox function is just identity, isn't this like equivalent to taking more aggressive step size?
Okay, so in this case, if the prox function is the identity, then I'm taking this to be my xk up there, right? It's not really equivalent to taking a more aggressive step size because it's not clear that this direction, which is the direction that we traverse to get to xk minus 1, would necessarily be the same direction as the gradient update. Right? So this is taking kind of two things into account. There's the direction of the gradient, which is, in this case, this is minus g of xk minus 1. And there's also the direction that we travel to get to xk minus 1. So if I take a more aggressive step size from xk minus 1, I'm just going to be traveling along this line.
You know, the previous iteration.
So maybe I can try to, you're evaluating the gradient at y, and you're evaluating the direction you're traveling from the last x. So you're evaluating them at different points. So it's not quite the same.
Question?
Is this somehow related to
Conjugate
conjugate gradient?
gradient descent. I wouldn't actually relate the two in my mind, but it might be. Maybe you'd have to ask me after class or something. Do you have an answer for that?
So I think conjugate gradient satisfies the same prescription that you're making an extra step based on the difference between the last two iterates. You can write it in that form. But the theoretical results that have been proven about conjugate gradient are different, mostly because I think people analyzed it under different assumptions.
Other questions? Well, it can't be true that CG is faster than this in terms of an order of convergence because this achieves the optimal convergence rate.
Well, but then
Practical terms, yeah, I don't know how I'd answer that. I mean, acceleration can be very finicky. We're going to kind of cover that later. It can work really, really well, and it can also work not so well depending on the situation that you apply it in. These are all good questions. Okay, so let's go back to this example. I'm trying to solve the logistic regression problem. Okay, there are lots of ways to do this, but this is one way. And there's 30 observations here and 10 predictor variables. That's my problem. And I applied two different things. I applied just regular gradient descent to this, and I also applied accelerated gradient methods to this. And gradient descent's in black, and the accelerated method's in red. Okay, so here I've plotted the number of iterations on the x-axis and the difference between my function value and the optimum on the y-axis. And we can see that generalized gradient descent gets to, say, an error of 10 to the minus 3 much, much faster than gradient descent. And if we let gradient descent run for a long time, we would probably convince ourselves that the difference here would be an order of magnitude in the number of iterations. Now I just did the same thing, but I just drew a different random sample of data, a different set of observations and predictor variables. And here's what it looked like. And this was now accelerated generalized gradient descent in red. And you can see that, well, I have these pretty characteristic ripples. Once you start working with this method, you're going to see that actually this is not uncommon at all for acceleration. People sometimes call this Nesterov ripples after Nesterov. And it's important to know this is not a descent method, right? So I've been trying to be careful calling it accelerated generalized gradient method and not accelerated generalized gradient descent, because it's not necessarily descending. We're not guaranteed that at all with the way we've actually prescribed the algorithm. So here's a way that we can reformulate what's going on, and it turns out this makes it a lot easier to prove the algorithm's convergence, and it makes it easier to connect what we did today in lecture with what you might read in one of the papers that I referenced at the end, because the formulations are a little bit different, but they're equivalent, as we're going to show. So I can think of now 3 steps and some constants theta k, and 3 steps in each iteration. The first step is that I take a convex combination of xk minus 1 and uk minus 1. Okay, uk is another variable. We haven't quite defined it yet, but you're going to see what it looks like in a second. Then I do the update to y. Okay, and then in the third step, I update u. And this kind of looks like what we did with y in the previous formulation of our generalized gradient. I take xk minus 1, and now I add on 1 over theta k times the direction that I'm traveling. Okay, so if we take theta k equals 2 over k plus 1, then this is actually exactly the same as what we did, how we formulated the algorithm in the first place. And how do we see that? Well, let's just plug in for u here. Okay, so what's uk minus 1? If that's uk, then uk minus 1 is xk minus 2 plus 1 over theta k minus 1 times xk minus 1 minus xk minus 2. And if I take 1 minus theta y, which is 1 minus theta k times xk minus 1 plus theta k times this, because that's uk minus 1, then it looks like this. Right? And now I can write that as, I can take this xk minus 1 from here, xk minus 1, and I'm going to have here plus theta k times 1 over theta k minus 1 times xk minus 1 minus xk minus 2. So let's just check that's the same. I have a minus theta k times xk minus 1, which was here. And I have a minus theta k times xk minus 2. I have a plus theta k times xk minus 2, which was here. And then these terms just come from these multiplications here. Okay, so they're the same thing. And now let's just plug in for what theta k was. So remember, theta k was equal to 2 over k plus 1. So this term is equal to 2 over k plus 1 times k over 2 minus 1. And that's just k minus 2 over k plus 1. Okay, so this formulation is no different. It just makes the convergence analysis a lot easier, and it ties what we've done in lecture to what you might read in a paper, if you ever are interested in looking this up. So here's the convergence analysis. The setup is the same as we've always had. The gradient is Lipschitz with some constant L. H is convex, and the prox function can be evaluated. And now, if we take the step size to be smaller than 1 of the Lipschitz constants, we get a very different answer than what we had before. Right? Before we saw k's in the denominator, now we see a k squared. And we also proved, actually as part of your homework, you've proved that essentially no first order method can do better than that. at large over all problems that have gradient Lipschitz, that have a Lipschitz gradient. So this achieves the optimal 1 over k squared rate for first order methods, and if we like to say it in terms of the error, it means that if I want an epsilon approximation to the minimum of my function, I need 1 over the square root of epsilon iterations, as opposed to 1 over epsilon, which is what we were seeing before. And that can be a very big difference. So we're not going to go through the convergence proof now. We may or may not go through it either at the end of this lecture or at the start of next lecture if people are interested in seeing it. So I just want to maybe see a show of hands. How many people actually would enjoy seeing that proof? That would feel satisfying because we did all this work to get here. Okay, I'd say it's probably like a third. So, yeah, who definitely does not want to see it? Like, you're sick of this stuff by now. It's not going to offend me. I don't care. Trust me. Okay, that's actually less than the people who wanted to see it. We'll make a game time decision next lecture, at the end of this lecture, as to whether or not we're going to prove that. The steps are here. Regardless of whether we prove it or not, the steps are in the lecture notes. So if you follow them carefully, you'll be able to get through the proof. And if we don't cover it, maybe one of the TAs will go through it in recitation. Yeah, so we're just going to skip this stuff. Backtracking. How do you do backtracking with acceleration? This is actually not an obvious answer. So with generalized gradient method, there was a way to do that. We just defined the generalized gradient, and we just basically plugged in what we knew for backtracking with gradient descent into this generalized framework. It's not so simple with acceleration, and there's actually several strategies for backtracking that people use. The reason is the proof that for acceleration having a convergence rate of 1 over k squared is different than the proof for gradient descent having a convergence rate of 1 over k. So we actually need kind of different criteria for our backtracking algorithm to satisfy in order to maintain the same rate. And those aren't kind of trivial like they are for gradient descent. So like I said, there's several kind of complicated strategies for how to backtrack with acceleration. Here's a simple one. The reason why people try to do more than this is because it requires at every iteration the step sizes you choose to be decreasing. So that's kind of restrictive because if you choose a small step size at step 3, then for the rest of the algorithm, you're going to be taking pretty small step sizes. So if you're interested in implementing this in practice and you want to use backtracking, you may want to look at some of the references I put at the end of the lecture. I think we're also not going to cover the specifics of why we need these two steps because they have to do with the convergence proof, but I'm just going to give you the prescription now. Basically, when we look through the convergence proof, we're going to see that we need two things to still hold if we choose the step size adaptively. And those two things are these two inequalities here, and we just define backtracking to be something that satisfies those two inequalities. So here's what it looks like. We fix some parameter beta less than 1, and we fix some initial step size t0, just like we do in regular backtracking. And then at each iteration of the algorithm, okay, we're going to replace the x update, which is the computation of x plus in my notation, with the following. We're going to start with the step size being equal to what it was at the last iteration. So this is different from regular gradient descent because we always started it being 1, for example, each iteration of gradient descent. But here we force them to be monotone, non-increasing. And then we're just going to go ahead and we're going to try to update the prox using y. So we're going to try to update x using y in the prox function. And this was kind of like the exit condition that we had for regular gradient descent. And with acceleration, it's a little bit different. It says that if our g doesn't decrease enough, g was the smooth part, by this amount, then we're going to continue shrinking t by a factor beta and updating x. Okay, and once g decreases enough compared to where it was at y, then we're going to stop. That's our exit condition. If you look carefully through the notes, we needed basically two things to work for the proof to be the same. So under the same conditions that we had in terms of the gradient being Lipschitz and the prox function being valuable, with this prescription for backtracking, we get the same convergence rate as we did for fixed step size. Okay, so I went over that kind of quickly, but in order to understand that, I think deeply we need to see the proof. So if we go back and do the proof, we might go back and look at this too. Okay, so here comes some of the applications now of acceleration. So this is the problem we've seen many times, and maybe you're also sick of this problem, but for first order methods, they tend to work quite well in this sparse regression setting, and that's where a lot of them first started being used in statistics and machine learning, so that's why I'm covering this example. So we're looking at the lasso problem again. It's the same as we've looked at for a few lectures now. And it splits up into G plus H, or that's G and that's H, smooth and non-smooth. And we derived this thing called ISTA last time, which we used generalized gradient descent on this problem. And it stands for iterative soft thresholding algorithm because we repeatedly apply this soft thresholding operator to the current point plus something like the inner product of our predictor variables in A with the residual. And we just keep repeating that, and that gives us, after a while, a lasso solution or a minimizer of this problem right here. Now if we apply acceleration, then we get FISTA. And the F here stands for fast. So it's the fast iterative soft thresholding algorithm, and it looks like this. We have two steps we keep repeating. I'm going to use V instead of Y because we already have Y for the response there. We just choose V to be the point that we're at, xk minus 1 plus this carefully chosen multiplier, k minus 2 over k plus 1, times the direction we're heading. And then we do our soft thresholding update to V, and that gives us x. Okay, and in case we've forgotten, why is that soft thresholding here? Well, that's because in this case, this is the prox operator at t. The soft thresholding function is the prox operator. In other words, the prox here, which is the minimizer of the following problem, 1 over 2t times x minus c squared plus h. H here is the 1 norm. Okay, that's what the prox function is. I can also write that, doesn't matter, I can multiply by t, and it won't change the minimizer. Okay, that's its equivalent formulation of the minimizer, and we showed when we studied subgradients that the optimal z here is just what happens when I take x and I soft threshold it, but I soft threshold it by an amount lambda t here because that's my multiplier on the 1 norm. Okay, so that's where this came from. This is just generalized gradient, in case we've forgotten. Yeah? Are you talking about the slides or here? The last x. Oh, yeah, thank you. That's a k minus 1. Yeah. Okay, so how does this compare? Actually, first I just wanted to mention, if you happen to read the paper that I'm referring to here, they use FISTA not for this problem, but for any problem that you use acceleration on. So it's a general term they use for any functions g and h, which I find kind of confusing because for an arbitrary h, it's not soft thresholding anymore. It's something different. But that's why I'm reserving FISTA to be used in problems where the penalty is the 1 norm. So like on your next homework, you're going to be implementing FISTA for a problem where this is no longer squared error loss, but you still have a 1 norm, and we're still calling it FISTA and ISTA because they're still doing this iterative soft thresholding. Don't be confused if you hear people throwing on these terms for acceleration in general, because that's how they are kind of originally coined, but it's somewhat of a misnomer in general. So here's how this compares. I did a short experiment on my computer. I took 100 lasso problems. 100 different times I drew a lasso problem. Here the number of observations is 100 and the number of variables is 500. Okay, so we have many more variables and observations. This is a situation in which we actually would want to use the lasso, right? Because least squares, for example, is not well defined in this situation. And I applied ISTA and I applied FISTA 100 times to each problem, and I recorded how fast they converged. So every kind of light-colored thin line here is a different repetition of this experiment, and the thick lines are the averages over 100 repetitions. So if you want us to look at the thick lines, here's ISTA and here's FISTA. FISTA converges a lot faster than ISTA, right? It's an order of magnitude faster, essentially. If we want to get down to an error of about 10 to the minus 4, we need about maybe 350 iterations for FISTA, and it's looking like it's going to take a lot more than 1,000, probably more like 3,000 at least, to get to 10 to the minus 4 if we used ISTA. Okay, and I did the same thing here with logistic regression. So in this case, I had 100 observations and 500 variables, but because I had many more variables and observations, logistic regression is not well defined for the same reasons you can think of as least squares being not well defined in that case. So I actually added an L1 penalty. So I took the function now to be f of x equals, I'll write censored again, I guess, plus lambda times the L1 norm. And you're going to figure out what that should be on your homework. But I took the logistic regression log likelihood, or actually the negative log likelihood, and I added an L1 penalty to it, and I solved that problem 100 times with ISTA and with FISTA. Okay, and the difference in implementing these two is really not any different, right? One involves, for this particular example of these lasso logistic regression and just lasso regression, one involves soft thresholding, the other involves basically adding a vector with a difference and then soft thresholding. So there's really no difference computationally between the two of them. I'm also not using backtracking here, so I'm not having to kind of worry about any complicated backtracking scheme. But the convergence rates are drastically different. You can see it's pretty much the same story here between ISTA and FISTA. I would have had to wait a lot longer on my computer if I wanted to get as good a solution with ISTA as I would have with FISTA. Yeah, question?
We're just curious about the previous slide.
Yeah.
We're just curious about the instance of ISTA that just at 800 abruptly went to...
Are you talking about this one here that comes down very quickly?
Yeah.
So I have a reason why I think that's true, but I'm not sure how rigorous it is. Well, actually, it has to do a bit with maybe with something I'm going to be saying it later at the end of this lecture. But sometimes, if a problem is well conditioned, then it doesn't matter whether you're using acceleration or not. You'll do very, very well if in this case the lasso model for this particular repetition happened to be something that was full rank and well conditioned. So suppose that it was finding a solution that was non-zero over only 50 of 500 of the variables, and those 50 were not very correlated, then it's going to be the case that any gradient method is going to work very, very well in that case. Okay, but it didn't happen in all the examples because I could have been choosing lambda here to be high enough that it actually on average was big models. But for this particular repetition, it happened to be a pretty small model, and that small model was well conditioned. So I'll say that again at the end of the lecture more precisely. But there's some kind of current research that investigates what happens if not the function itself is strongly convex, say, but the function is strongly convex in a neighborhood around the current iterate, or a neighborhood around the solution. You might imagine that the solution is something that is 0 in 450 variables and non-zero in the other 50 variables. And if the function is strongly convex around that solution in a big enough neighborhood, if I happen to get into that neighborhood, I can converge very quickly. So I think that might be something to do with what's happening here.
So to add to that, you have to find that neighborhood, right? So if PISTA or ISTA is lucky enough to get to knowing what the correct 50 non-zeros are, then it can converge quickly. But if it, is swapping out things being 0 or non-zero, then it's probably not going to do that great convergence rate.
And I think, like I was saying, for this particular example, I chose lambda to be small enough that that didn't happen most of the time. So the estimates here were maybe larger than 50 or 10 or however much it needed to be. So in most of these cases, that special case wasn't happening when I ran Ascent Vista. Okay, let's take a short break, and then we're going to go back to talking about is acceleration always useful. Okay, let's get back to lecture. So we've seen that acceleration provides us with a rate of 1 over k squared, which is optimal. We can't do better than that at large over the problem class that we're interested in. So you might think we should always use it. Right? We have an optimal method. Why not? Any problem you have, acceleration. Just don't even think. But it's actually somewhat of an important question to address. Is acceleration always useful? And in what situations would it actually maybe be not so useful, or can it even hurt if we use acceleration in some situations? So here's a couple of examples I'm going to talk about in which acceleration doesn't help very much, and actually in the second example, it can hurt us to use acceleration if we weren't thinking about the problem very carefully to begin with. So in my first example that I'm going to talk about, I'm thinking about we want to solve a problem that has a tuning parameter associated with it, lambda. So you can think of the lasso problem, say, or suppose I'm just minimizing a problem that looks like this. F of x equals g of x plus lambda times h of x. Suppose I want to minimize this problem for some value of lambda, and then I want to do it again for another value of lambda, and so on and so forth for many values of lambda. Okay, so why might I want to do that? If we're thinking about regression again, sparse regression, this might look like this. And of course, as I change lambda, I'm going to set more entries of my estimate x to 0. And if I don't know how many I want to have 0, which is typically the situation in all of our applications, I want to try this over several values of lambda, and then I would apply, after that, some method to select among those solutions x hat. Okay, so let's just maybe do a quick thought experiment. If I'm in the regression setting, and suppose I tried out like 100 values of lambda, and at each value of lambda I got a solution x star. Let's suppose that or here I call it x hat, I guess, of lambda. Let's suppose my goal now was to build a vector of coefficients that predicted the best. My goal was that if you gave me a new y that I thought also followed this same relationship as the data that I trained on, I want to be able to predict best that y from its x's without having seen that y. How would I be able? What would be one way I could actually choose among all these different values of lambda the correct estimate? What's that? Cross-validation, right, yeah. So I would, for example, I would split up my observations into a bunch of parts, and then I would compute the solution, say, let's make it very simple. Let's suppose I just split it in 2 parts. I have 100 observations, so I put 50 over here and 50 over here. On these 50, I go ahead and I solve the problem for 100 different values of lambda. So I get 100 solutions. And on each of these solutions, I see how well they actually predicted the y on the other half of the data that I left out. Okay, and then I pick that value of lambda and the corresponding estimate as the one I'm going to carry forth in my analysis, whatever my analysis was. So in this situation, I'm solving a problem that looks like this over many values of lambda. Right? And if I start at a very high value of lambda, then most of the entries of x are going to be 0, so you might believe that actually the algorithm would converge faster. So I might start at a very high value of lambda, and then I would decrease lambda sequentially and solve at each smaller value of lambda. So there's something we can use in this case called warm starts. This is an important thing to remember when you're using iterative algorithms. It means that instead of initializing at 0 in future problems where we want to solve for a smaller value of lambda, I should just go ahead and initialize at the solution to my problem for the previous value of lambda. Okay, so for my largest value of lambda, at lambda 1, I'll initialize x0 equals 0, and I'll solve to get x hat of lambda 1. But then at lambda 2, if lambda 2 is just a little bit smaller than lambda 1, there's no point in starting at 0. I might as well just start at x hat of lambda 1. Right? And there's some kind of underlying assumption that we have here that the solutions to these problems are continuous in lambda. Right? If I move lambda a bit and the solution was like way, way different, then this warm starting scheme wouldn't make any sense. But it's generally the case, it's the case in the lasso problem, and you can prove for a bunch of different problems that they are continuous in lambda. So it makes a lot of sense to do this, and it can help tremendously in practice. So we just kind of repeat this strategy. This is called warm starts. And if you just pass it a fixed vector like 0 at each point, that's called a cold start. Those are the terms that people usually use. So a lot of people have observed that if you do warm starting over a grid of lambda values, it almost makes no difference whether you use acceleration or not. For the lasso problem with squared error loss, for logistic regression, for a lot of these problems. Acceleration can help a lot if you're cold starting at a fixed point, but if your goal is to solve it over a sequence of lambda values, the total amount of computation you'd spend is going to be pretty similar between acceleration and no acceleration. And in some cases, it can actually hurt his acceleration. Okay, so in this case, you should think pretty carefully, am I in a situation where I have not a lot of extra information in terms of where I should start? Acceleration might be useful. If I do have that extra information, you might try no acceleration and see how bad the performance is before you implement acceleration. Here's an example in which acceleration and even backtracking can be harmful. A question about that?
Why the model is not overfitted here because we are overtraining the model?
Why are we not overfitting?
Yes, because you use the previous answer and start it again.
Yeah, so I mean, using the previous answer has nothing to do with overfitting. So you can think about, there's two different goals. The first goal is all I want to do is I want to optimize my criterion for a fixed value of lambda. And there's no way to overfit that or over-optimize. I just want the solution. Once I have those solutions, then I can evaluate among them to see which one I believe gives me the right balance of sparsity and fit to y. And if I choose one that has a too close fit to y, not enough sparsity, then I might be overfitting. But within the actual procedure of solving the problem, there's no overfitting concern.
Kind of related to that, can you say anything about how this works in non-convex problems? Like if you were to initialize with previous values of lambda and you're worried about local minimum?
So people do it in non-convex problems, but a good example of a non-convex problem that's not continuous is subset selection. So if I look at this problem, I guess we can think about it in the Lagrangian form now if we want to. Okay, so here's a non-convex problem that does the same thing, but instead of penalizing with the 1 norm, I'm counting the number of non-zero coefficients of x. If I change lambda a bit, then actually my solutions here can jump. So it's not continuous anymore. And again, well, I guess now you have to be concerned about local minima, but there's no reason why warm starting in general would help you. You can think about it like if I change lambda a bit, I might go from a model that has 3 non-zeros to 4 non-zeros. And I'm just doing regression basically now on those variables. I can get a very different answer. If I choose these 4 or these 3, the regression coefficients can be quite different. I'm not sure the interplay between local minima and warm starting. I'm not sure whether that's going to work in your favor or not in your favor. Good question. Yeah.
Would it make sense then to reverse the order of lambda so they start with the small one first? So it's the least constraint at the beginning and then increase the number of zeros in that particular problem.
And this one right here, the non-convex one? But I mean, the discontinuities go both ways. I'm not sure why one would be easier than the other to deal with.
I guess intuitively it's easier to project them to a dimension rather than subtract out the zero.
Yeah, it could be. I'm not quite sure how different that would be, but it probably would be different because the solutions aren't unique. So you would get a different path going both directions. So maybe you would see how different they are in practice, and maybe one of them works better or not. Generally speaking, if a problem is highly constrained, then we can solve it more quickly. That's not written into our convergence rates. When we talk about coordinate descent later in the class, we're going to see that's the method that actually explicitly takes advantage of sparsity. So if we have a problem in which lambda is huge and the true solution has 5 out of a million non-zero coefficients, then we can solve that a lot faster than a situation where lambda is, reasonable and we have 5,000 out of a million coefficients non-zero. So we're going to see kind of more explicitly in other methods that it's easier to solve problems in which the solution is constrained. In general, with first-order methods, it's also true. Like I said, it's not actually written into it's not hard-coded into our convergence rates anywhere. But if you can, you want to start the problem at that end, generally. So here's an example in which acceleration can actually be harmful. We're going to return to the matrix completion example. And like we talked about at the start of class, this is what our updates look like. I do this matrix soft thresholding to a matrix that's composed of, in two parts, one by the observed A and one by the estimated variable X. In this case, this matrix soft thresholding operator, this required the SVD. Right? It was defined in terms of if you give it some matrix Z, it gives you back something like U times sigma of lambda V transpose, where U sigma V transpose was the SVD of Z, and sigma had its diagonal elements soft thresholded. So I sometimes will write the maximum between this and 0 as just the positive part. Okay, so that's how we define this matrix soft thresholding operator. In this case, it's pretty expensive. It requires an SVD. That's not nearly as cheap as something like soft thresholding. Okay, so now let's think about backtracking and acceleration carefully. In backtracking, every loop of backtracking, let's just say even without acceleration, it evaluates the generalized gradient. Right? Because the backtracking uses this quantity. Each evaluation of the generalized gradient is another call to the prox function. So it's another SVD we compute. So for matrix completion, we can't afford this. We can't afford in each iteration to be computing several SVDs. Right? That can get out of hand. So if we have a fixed step size rule that's as large as we can get away with, we might as well use that. And remember, in matrix completion, the Lipschitz constant was 1. Right? So we just took t to be equal to 1 over L, which is 1, and we fixed that as our step size. So backtracking could actually hurt us in this example. How about acceleration? In acceleration, it changes the argument we pass to the prox function. It usually is like this, x minus t times the gradient. With acceleration, it's y minus t times the gradient, where y was some combination of x in the previous iterates. So let's look at matrix completion again. What's x minus the gradient for matrix completion? That's equal to this. The projection of A onto the observed entries. It means I just take the entries of A that were observed and 0 everywhere else, plus the projection onto the complement of the observed entries of X. So how do I compute the SVD of this? We need to evaluate the prox function of this. That's an SVD. Well, actually, there's a nice way to do that because this matrix is sparse. We typically only observe few entries, so omega is pretty small. So this matrix is sparse, has a lot of zeros. And this matrix, by construction, is low rank. The previous iterate x, we've done some rank reducing step, so it's low rank. And there's some nice algorithms to compute the SVD of a sparse plus low rank composition of matrices. So we can do that fast. What happens if we use acceleration? In that case, it looks like this. Projection onto omega of A plus the orthogonal projection of Y. This is sparse, but that's not necessarily low rank, right? Because now Y is a combination of previous iterates. So if I take two low rank matrices and I combine them, I get something of higher rank. And if I use the version of Nestrov's acceleration with infinite memory, not just combining the previous two iterates, but all iterates, then it's going to be hopelessly high rank. I'll be combining, if I'm at iteration 100 matrices, I'll get something of very high rank, and I can't compute the SVD fast anymore. So that's why if you look at soft compute, which is a pretty simple algorithm, and you compare it to something that's pretty fancy, it uses acceleration and backtracking that are trying to be tuned as finely as possible to the matrix completion problem, soft compute pretty much dominates in terms of its runtime. So this is a figure from the paper in which soft compute was proposed. Here's a method that has a worst case rate of 1 over k squared. So in principle, it should be a lot faster than soft compute. But in practice, because these prox calls are very expensive, you can see that the dashed line, which is the accelerated version, and the blue line, which is the soft compute version, they're very different. Okay, so soft compute can run a lot faster. So this is not a singularity. There are lots of examples where acceleration might not be the best idea. So yes, it's a great general tool, and it's something that's very kind of popular. It's come up in the last 20 years, and people are starting to use it a lot, and it's really helped a lot, but it's not a big hammer that you can apply to everything. You have to be kind of careful about what you're going to pound with that hammer, because sometimes it's not going to work so well. I don't have time to get to this, so I guess we're going to end here. And I put a bunch of references for all the stuff we've talked about. There's been a lot of papers on acceleration, so you can take a look through that if you're interested. Okay, see you on Thursday.